The LM4F 120H5QR has 4 different types of memory: flash, SRAM, EEPROM, and ROM. In Chapter 8, you'll learn about the different features and capabilities of the flash, SRAM, and EEPROM. You'll also learn how to use bit banding and how to use the Memory Protection Unit, or MPU. This diagram shows you a little bit about the flash, SRAM, and ROM control. On the far left is the Cortex M4F. You'll notice that there's a separate instruction code and decode bus for instructions and for data. So this is a Harvard architecture inside to the ROM and the flash. You'll notice the system bus goes down to the bridge to the SRAM array. Yet up at the top we have ROM control to the ROM array. We have all of these buffers and control type logic and settings to talk to the flash array. There's also down in the bottom we have the flash protection and then a series of user registers. The EEPROM control is separate because it's in peripheral space. You'll see the EEPROM array with the separate blocks on the right hand side, a security setting, a separate program once we've been able to go through the security, and then the control registers that control the size, the page, the offset, how we're writing to it, and so on. Remember, the EEPROM block is connected to the advanced high performance bus for maximum speed. Flash memory on the LM4F 120H5QR is 256K long, and it's single cycle to 40 MHz. That memory starts at all zeros as shown in the memory map below. It's organized into 1K independently erasable blocks. Like I showed you in the previous slide, the code fetches and data accesses occur over separate buses. You don't have to worry about it being a Harvard architecture machine. This just speeds you up. Below 40 MHz, that flash access is single cycle. Above 40 MHz, there's a prefetch buffer that fetches 2 32-bit words per cycle. Remember that we're running thumb2 instruction code, which can be either 16 or 32. So at a minimum, we're able to grab 2 32-bit instructions per cycle, and that's at a minimum. So in straight line sequential code, there's no wait states involved. So the only problem is going to be if you hit a branch. We have branch speculation, that on one direction of the branch, it does a speculate to see if you're going to go in that direction, and it's going to avoid a wait state in that direction. So only in one branch, one side of the branch, are you going to incur a wait state. The write and execution protection are available on the flash so that you can configure this so that people can't write into it without a password, and it has a very simple programming interface, as we'll see in the lab. EEPROM is 2K of memory starting at, and this is in the peripheral space, 0x400AF000. It's accessible as 512 32-bit words. That's broken up into 32 blocks of 16 words, that's 64 bytes in there, with access protection per block. We get to an endurance level of 500,000 writes with built-in wear leveling on this, so you won't be wearing out a single bit. Lock protection is available for the whole peripheral as well as per block using 32-bit to 96-bit codes if you like. We have available interrupt support for write completions so that you don't have to poll to make sure that you've finished writing to the memory. Random and sequential read-write access is possible, 4 cycles maximum per word. If you're doing random, that'll be 4 cycles. If you do sequential, it's less than that. The SRAM on the part, it's 24K of SRAM, full speed 80 MHz, starting at 20 million, 20,000,000. That physical memory is bit banded into 22 million, 22,000,000. And of course, SRAM can hold code or data. You can execute out of SRAM if you choose to do so. As we've mentioned before, all M4 devices have bit banding. This reduces the number of read, modify, write operations. SRAM and peripheral space use an address alias to access the individual bits in a single atomic operation. So SRAM, the physical memory, starts at a base address of 0x20
0000000, call that 20 million. The bit-banded SRAM, the bit-banded address alias of that starts at base address 22 million. Peripheral space starts at a base address of 40 million. The bit-banded peripheral space starts at base address 42 million. So if you want to calculate the bit-banded alias, you use this following formula. So the bit-banded alias is whatever the base address is of the piece of memory that you're looking for, plus the byte offset times 0x20, that's 32, plus the bit number times 4. So if you're, for example, if you're looking for to calculate the bit-banded address of bit 7 of address 20,000,000,000, that's going to be that base address 20,000,000,000 plus the offset, which is 2000 hex, times 0x20, that's times 32, plus bit 7 times 4. Add all that together and you're going to get a bit-banded address of 0x22040001C. The LSB of that location will be bit 7 of physical address 20002000. The memory protection unit defines 8 separate memory regions plus a background region that's accessible only from privilege mode. These regions of 256 bytes of more get divided into 8 equal-sized subregions. You can set up the definitions for every one of those regions, including that's going to include the location of the region, the size of the region. What access permissions do you want to allow? Do you want to allow execution? Do you want to allow code? Do you want to allow data? Do you want to not have any access? And what other memory attributes do you want to specify? Accessing a prohibited region in memory is going to cause a memory management fault. We're going to see that in the lab. Accessing some of the registers that allow you to program the memory protection unit are protected by a privilege level. We're going to talk about that in the next slide. The Cortex-M4 has 2 different privilege levels. Those levels offer additional protection for software, particularly if you're using operating systems. In unprivileged mode, your software has limited access to the priority mask register, no access to the system timer, the NVIC, or the system control block, and possibly restricted access to memory or peripherals. Privileged software has use of all the instructions and has access to all the resources. ISRs operate in privileged mode. Threaded code, like in an operating system or standard, operates in unprivileged mode unless the level gets changed via the thread mode privilege level bit in the control register.
In Lab 8, you'll create code to write to flash and to read-write EEPROM. You'll also experiment with bit banding, then you'll configure and use the memory protection unit. In Lab 8 Step 1, we've already created the Lab 8 project for you with an empty main.c, a startup file, and all necessary project and build options set. Maximize Code Composer and click Project, Import Existing CCS Eclipse Project. Make the settings shown below to import Lab 8 and click Finish. Make sure that the Copy Projects into Workspace checkbox is unchecked. Click Finish. Expand the project by clicking the plus next to Lab 8 in the Project Explorer pane. Double-click on main.c to open it for editing. Let's start out with a straightforward set of starter code. Copy the code below, the driver lib and include files, and paste it into the top of your main.c file. The int main void does the setup on the clock. The peripheral enable enables the GPIO. There's the outputs. A pin write of 0 to the pins to make sure the LEDs are off. A little sys delay to give us some time, and then a while loop. So you should already know what all that code does. No big deal. Save your work, if you're having any problems, this code is in your Lab 8 CCS folder as main1.txt. In step 4, we need to find a writable block of flash memory. Right now, that would be flash memory that does not currently hold the program we're executing. Under Project on the menu bar, click Build All. This will build the project without attempting to download it into the LM4F 120 H5QR memory. As we've seen before, Code Composer Studio creates a map file of the program during the build process. Look in the debug folder of Lab 8 in the Project Explorer pane and double-click on lab8.map to open it. Find the memory configuration and segment allocation map sections as shown below. From the map file, we can see that the amount of flash memory used is 0x086A in length that starts at 0. This means that pretty much anywhere in flash located at an address greater than 0x1000 for this program is writable. So let's play it safe and pick the block starting at 0x10000. That's 10000. Remember, flash memory is erasable in 1K blocks. Close the lab8.map file. In step 7, back in main.c, add the following include to the end of the include statements to add support for Flash APIs. So that's #include driverlib flash.h. At the top of main, enter the following 4 lines to add buffers for read and write data and to initialize the write data that we're going to use. So we have a long set of data that we're going to use for the transmit or the write, and then a set that we're going to use for the read, and then we're going to set it to 1, 2, 3, 4, and so on, something that we're going to recognize. Just above the while loop at the end of main, add these 4 lines of code. Now, earlier in the material, I told you that the set of Flash programming APIs was easy to understand. So how about this? Let's, in the first one, erase the block of Flash that we identified earlier. There's the 0x10000. We want to program the data array we created to the start of the block of the length of the array. So there we're programming our data to the block of that size. The third instruction lights the red LED to indicate that we were successful, and then delay about 2 seconds before the program comes to a halt inside the while loop. In step 10, your code should look like the code below. If you're having any issues, this code is located in the Lab 8 CCS folder as main2.txt. In step 11, click the debug button to build and download your program to the LM4F 120 H5QR memory. Ignore the warning about the variable PUL read not being referenced. When the process is complete, set a breakpoint on the line containing Flash program API function call. We'll worry about the pull read thing later. We're not reading it now. In step 12, click the resume button to run the code. Execution should quickly stop at the breakpoint. On the CCS menu bar, click View Memory Browser. When the window comes up, enter 0x10000. 10000. Excellent. So if you're aware of how Flash works, when it's erased, it should be read as all ones. When you program Flash, you only program zeros. Because of that, writing to unerased Flash memory will produce completely unpredictable results. In step 13, click the resume button to run the code. The last line of code before the while will light the red LED. So the red LED is lit on the board. Click the suspend button. Your memory browser will update, displaying the successful write to flash memory. So those values, the ones that we had initialized earlier, it should be pretty clear that those are there. Remove your breakpoint from the code. You can double click on it or remove all breakpoints. In step 15, make sure you've clicked the terminate button to stop debugging and return to the edit perspective. Bear in mind, if you repeat this exercise, the values that you just programmed in Flash will remain there until that Flash block gets erased. In step 16, back in main.c, add the following line to the end of the include statement to add support for EEPROM APIs. That's driverlib EEPROM.h. In step 17, just above the while loop, enter the following 7 lines of code. The first one turns on the EEPROM peripheral. Remember that the EEPROM is in peripheral space. Step 2 performs a recovery, EEPROM init, if the power failed during a previous write operation. Flash memory and EEPROMs are prone to an issue if the power manages to go down during a write cycle. So this will perform a recovery for that. Step 3 is a EEPROM mass erase. This erases the entire EEPROM. Now, of course, this isn't strictly necessary because, unlike Flash, EEPROM does not need to be erased before it's programmed. The only thing is this is going to allow us to see the result of our programming more easily when we do this in the lab. The fourth one reads the erased values into the read array that we set up. The fifth one programs the data array to the beginning of EEPROM of the length of the array. The EEPROM read reads that data into array PUL read, and the seventh one turns off the red LED and turns on the blue. So when we see the blue come on, it means the entire process will have completed properly. One thing I'd like to mention here is you might think that we'd be able to open up the memory browser and take a look at the EEPROM, but it's actually a peripheral. You have to read it using code. You really can't go in and take a look at it in the memory browser. So in step 18, your code should look like the code that you see in the box below. If you're having issues, this code's located in the Lab 8 CCS folder as main3.txt. In step 19, click the debug button to build and download your program to the LM4F 120 H5QR memory. Like I said, CodeComposer does not currently have a browser for viewing EEPROM that's located in the peripheral area. The code we've written will let us read the values and display them as array values. In step 20, click on the Variables tab and expand both of the arrays by clicking the plus next to them. Excellent. Right-click on the first variable's row and select number format hex. Do this for all 4 variables. In step 21, set a breakpoint on the line containing EEPROM program. We want to verify the previous contents of the EEPROM. Click the resume button to run to that breakpoint. Since we included the EEPROM mass erase in the code, the values read from memory should all be Fs, as shown below. So you can see the PUL read are all Fs down at the bottom. In step 23, click the resume button to run the code from the breakpoint. When the blue LED on the board lights, click the suspend button. The values read from memory should now be the same as those in the right array. So you can see that on the bottom there, they've both changed. Some further double EEPROM information. In step 24, double EEPROM is unlocked at PowerUp. You can implement a locking scheme if you like. Your scheme, if you choose to use one, can be simple or exceptionally complex. You can lock the entire double EEPROM, or you can lock individual blocks. You can enable reading without a password and writing with one if you desire. You can also hide blocks of double EEPROM, making them invisible to further accesses. Double EEPROM reads and writes are multi-cycle instructions. The ones used in the lab code are blocking calls, meaning that the program execution will stall until the operation is complete. There are also non-blocking calls that do not stall program execution. When using those calls, you should either poll the double EEPROM or enable an interrupt scheme to assure that the operation completes properly. In step 26, remove your breakpoint, click Terminate to return to the CCS Edit perspective, and close the Lab 8 project. In Lab Step 27, the Launchpad board Stellaris examples include a bit banding project. Click Project, import existing CCS Eclipse project, make the settings shown below, and click Finish. We'll be importing the bit banding project from the Launchpad folder. Notice that it will automatically copy the project into the workspace for us. In step 28, expand the project in the Project Explorer pane and double-click on bitband.c to open it for viewing. Page down until you reach Main. You should recognize most of the setup code, but note that the UART is also set up. We'll be able to watch the code run via UART printf statements that will send data to a terminal program running on your laptop. Also note that this example uses ROM API function calls. By the way, you could have done that in any of these, and you saw how to do that back in the ADC lab. In step 29, continue paging down until you find the for UL index equals 0 loop. This 32-step loop will write 0x DEC AF BAD into memory bit by bit using bit banding. This will be done using the hwregbitw macro. Right-click on hwregbitw and select Open Declaration. The hwregbitw macro is an alias from hwreg, which is C code for bit band alias. This is a calculation for the bit banded address of bit B in location X. hwreg is a macro that performs a hardware register or memory location, that programs a hardware register or a memory location with a value. The loop in bitband.c reads the bits from 0x decaf bad and programs them into the calculated bit band addresses of G_UL value. Throughout the loop, the program transfers the value in the variable to the UART for viewing on the host. Once all the bits have been written to that register, the variable is read directly, all 32 bits, to make sure that it's actually 0x decaf bad. There's another loop that reads the bits individually to make sure that they can be read back using bit banding. So you can see that this C code here in this register is the exact same calculation for the bit-banded alias address of an actual address in SRAM that we saw earlier in the presentation. In step 30, click the debug button to build and download the program to the LM4F 120H5QR flash memory. So here, go ahead and open up your terminal program in either step 31 or step 32. Actually, we're using Windows XP, but we really like PuTTY, so we're using PuTTY. In step 33, click the resume button in CCS and watch the bits drop into place in your terminal window. You'll need to be able to see both of those at once. There we go. Click the resume button. So it will take about 30 seconds with all the delays on here to have this thing come up and say, eventually, it will program in decaf bad. So there's each one of the bits in that section. Here's the B, here's the A, and we'll come in with the last D. There'll be a final check, success. Good. So we're sure that it works here. Go ahead and close your terminal window. Click Terminate in CCS to return to the CCS edit, the editing perspective, and go ahead and close the bit banding project. In step 35, the Launchpad board Stellaris examples include an MPU fault project. Click Project, Import Existing CCS Eclipse Project. Make the settings shown below to bring in the MPU fault folder from the Launchpad folder. And again, note that this project will be automatically copied to your workspace. In step 36, expand the project and double-click on MPU fault.c for viewing. Again, things should look pretty normal in the setup, so let's take a look at where things are different. Find the function called MPU fault handler. This exception handler looks just like an ISR because it is an ISR. The main purpose of this code is to preserve the address of the problem that caused the fault as well as the status register. A great thing to have when you're working with having exception faults in your code. Open startup ccs.c and find where MPU fault handler has been placed in the vector table. You can see it right up at the top. There's the MPU fault handler. Close startup ccs.c. In step 37, in MPU fault.c, find the main section. Using the memory map that's shown up at the top, the MPU region set calls, those API function calls, will configure 6 different regions and parameters for the memory protection unit. The code following the final MPU region set call triggers, or if it's not going to cause a problem, it doesn't trigger, the fault conditions. Status messages are then sent to the UART for display on the host. The MPU region set API call uses the following parameters. It says, first, what region number to set up. So we can look there at any one of the ROM MPU function calls. There's the ROM MPU region set. So if you look through the list, there's a region number to set up, the address of the region, and then a whole set of flags. The flags are a set of parameters that are ORed together that determine the attributes of the region, like the size, the execute permission that you want to give it, the read-write permission you want to give it, whether or not you want to disable any of the subregions, and then to enable or disable the entire region. So The size flag determines the size of the region and must be one of the ones that's listed in the workbook. The execute permission must be either execute or no execute, as shown in the permission flag. The read-write access are permissions applied separately for the different modes. The read-write access modes must be one of the following that's shown in the workbook. Each region is automatically divided into 8 equally sized subregions by the MTU. This is only on regions of 256 bytes or larger. Anything that's smaller is dealt with as a single region. Any of these 8 subregions can be disabled, allowing you to create holes in a region that can be left open, or you can overlay them with another region with different attributes. So you could overlay 2 regions and have the subregions completely different as a checkerboard if you wanted to. Any of the 8 subregions can be disabled with a logical OR of any of the flags that are shown, and the entire region can be enabled or disabled. So in step 38, start your terminal program as shown earlier. Click the debug button to build and download the program to the device. And we'll need to resize this so that we have both windows open. Excellent. So we're all set to go. Click the resume button to run the program. So here what we can see, the tests are as follows. What the MPU fault program attempts to do, it attempts to write to flash. So this should cause a protection fault due to the fact that this region has been set up in the code as read-only. If that fault occurs, the terminal program should show OK. In the next one, the attempt to read from a disabled section of flash. If that fault occurs, the terminal program should show OK. Next is an attempt to read from the read-only area of RAM. If that fault does not occur, the terminal program should show OK. And the last one is an attempt to write to the read-only area of RAM. If that fault occurs, the terminal program should show OK. When you're done, close your terminal program, click the Terminate button in CodeComposer Studio to return to the CCS Edit perspective. Close the MPU fault project and minimize CodeComposer Studio.